Welcome to our discussion on exponential functions. As always, you can fast forward until you see this slide in order to find the material you want to review. Let's start by defining an exponential function. An exponential function is any function of the form a to the x, where a is a positive number, right? It's greater than 0, and it's not equal to 1, because obviously if it was 1 raised to any power is just 1, right? So we have to have some number that's positive and can't be equal to 1. And if that's the case, if we have something of that form, we call it an exponential function. We say the base of the function is a and the exponent is x. Some simple examples would be, one of the most common ones, e to the x. But you could also have 3 to the x or 1/2 to the x, right? Anything other than 1. Here's some examples on how we can evaluate these things. So here's a simple f of x is 3 to the x minus 2. It's good to realize that all of this is the power, right? So if we want to find f of 4, we simply plug in 4 for x, get 4 minus 2, which is 2. And so now it's just going to be 3 squared, which is 9. Same thing for these, right? Just plugging them in for x. So as we saw, 3 squared is 9. When we plug in negative 2 for the second one, it's negative 2 times 10 to the x, right? So 10 to the negative 2, which is 1 over 10 squared, which is 1/100th, times negative 2, negative 2/100ths. And so on and so on and so forth, right? It's no different from any other function. If you want to evaluate them, it's just a matter of plugging in the numbers for what they ask. If you're dealing with powers, you have to remind yourself of some of those rules of powers, right? When you raise something to the negative 3/2 power, as we did here in our third example, example C, that's the same thing as 1 over, right? This thing is 9 to the negative 1, this 1 over piece, and then a power to a power, you multiply those powers, and now you have 9 to the 3/2 power. Well, 3/2 power means you're taking a square root and then cubing it. So if you square root 9, you get 3, and then 3 squared is 27. That's the easiest way to do that one. And then this last one is just raising something to a decimal, requires you to use a calculator. As I mentioned, we have to remember our rules of exponents. So if we have a to the x times a to the y, we have to remember that we add them, right? A to the x divided by a to the y, we subtract them, a to the x to the y, right? If we have a power raised to a power, that's when we finally multiply them. Remember, anything raised to 0 is 1. You can distribute a power, right? If you've got some product of things raised to a power, then each piece is raised to that power. And then a negative exponent is the same thing as 1 over that. And then, of course, you can kind of factor out the power. Because 1 is the same thing as 1 to the x, you can factor it out and say this whole thing is just to the x power. So you can see that what's happening here, another way to think about that, is this is a to the negative 1 to the x, right? Because that'd be negative x. And then a to the negative 1 is 1 over a, all to the power of x. That's how they're getting that in another way. Okay, how about graphing? Well, just like any other function, if you're asked to graph it and you can't use technology, then just plug in a bunch of points. Give yourself a simple XY table and plug in a bunch of x values, calculate the corresponding y values, and connect the dots with a smooth graph. Very simple. So here's the table. You plugged in negative 3, 2, 1, positive 1, 2, 3, and 0. You plot all those points, you connect the dots, and there's your graph of y equals 3 to the x. And that's a typical looking exponential function anytime a is bigger than 1. How about this one? Same idea, make a table, plot some points, and we get this, which is a typical looking function for when a is between 0 and 1, right? It has to be positive, so it has to be greater than 0, and it can't equal 1. So whenever you have a fraction, you get a function that gets smaller and smaller and smaller, right? It hugs down there on the x-axis, getting closer and closer to 0. And when it's greater than 1, you get a function that as you go to negative infinity, it gets closer to 0, but as you go to positive infinity, it blows up, right? It just gets super big, super fast. Properties of the exponential function. The domain of the exponential function is everything, right? As long as a is a positive number not equal to 1, we can raise it to any power we want. So negative infinity to infinity. And then the range of a to the x is always going to be 0 to infinity, both with round brackets. Look at our previous pictures, right? That one is going to be 0 to infinity, and that one's also going to be 0 to infinity. Okay? Next, we also know that because f of x plus 1 over f of x is just a to the x plus 1 over a to the x, which is a to the x times a. That's what this little box is supposed to be, a times. These will cancel, and you'll just get a. The y value change, by a factor of a. This is a. For each unit increase in x. So you basically get a straight line, right? You get y equals a, which is a straight line constant kind of thing. So if a is greater than 1, the growth factor is a. And if a is between 0 and 1, it's a slightly different property. So let's look at this one first. When a is greater than 1, we know f is increasing. So the graph rises to the right. So as x gets bigger, y gets bigger. As x gets smaller, y goes to 0. When a is between 0 and 1, we get that decay factor of a, right? It's reducing by a each time. And because they decrease by a factor of a, right, we should put little parentheses around it because it just looks like factor of and you're like, of what, right? Factor of a for each unit increase. So f is now a decreasing function. If you remember, this graph looks like that, and it levels off, right? So as x goes to negative infinity, right, as we go to the left, y blows up to positive infinity, and then as x goes out to the right, y gets closer and closer to 0. You'll remember that the other function, right, when a was bigger than 1, looks like that. And both of those are one-to-one functions because they both pass the horizontal line test, which means they both have inverses. Neither of them, right, neither versions have x-intercepts, so it never crosses the x-axis. So that means there's no value of x that will cause it to equal 0, which makes sense. You can't take a positive number and raise it to a power and ever have it equal 0. The graph is a smooth and continuous curve, and it passes through these points always. Negative 1 gives you 1 over a, 0 gives you 1, and 1 gives you a, right? From the previous numbers 4 and 5, we can conclude that the x-axis is a horizontal asymptote for every exponential function. If you recall what the two functions looked like, you had one that hugged here, and then one that hugged on the left, right? So they both came down and hugged the x-axis. Next, we can develop formulas for simple and compound interest based on these. So the interest rate is the percent charged for the use of the principal for the given period. What the heck does that mean? Well, the interest rate, which we normally denote by an R for rate of interest, right? You might think it should be an I for interest, but it's R for rate of interest, is always expressed as a decimal. So if you're paying 3% interest, you would express that as 0.03. And unless stated otherwise, the period is always assumed to be 1 year, and so therefore R is what's called an annual percent rate. Okay, so your interest rate is just the percentage charged each period, usually a year, that you have to pay. It's a fee you have to pay in order to borrow some sort of money. If you're only computing interest on the principal, then it's called simple interest. And you might be saying, well, don't you always compute interest on the principal? Yes, but simple interest means every year you're paying the same amount. So if you borrow $100 at 5% interest at the end of 1 year, you now owe $5 in interest, but you still owe the $100, so you technically owe $105. Now for the next year, year 2, if you don't pay them anything back, simple interest means you're still only charged another $5, 5% on the original principal of $100. Compound interest, which is what's more common, what's used in the actual real world, you now would have to pay that 5% interest on the new balance of $105, which would mean it would now go up. And that's how, credit card bills get out of hand very quickly, because they're like 29%. So here's your simple interest formula, very simple. I, being interest, right, is equal to the principal times the rate times time. And the rate and time here have to be in the same unit of measure. So if your interest rate is based on, it's an annual interest rate, and so let's just do an example. Let's say you borrow, how about $10,000? Okay, your interest rate is 5%, which we would always write as a decimal. And this is 5% annual, right? This is an annual rate. And let's say you're going to borrow it for, how about 66 months? Well, you can't have your interest rate in terms of years and your time in terms of months. They both have to be listed the same. And the easiest thing to do is make everything in terms of years, right? Or more specifically, make everything in terms of whatever your R is in terms of. So take 66 months and convert it to years. Well, 60 months is 5 years, right? And then 6 is half. So this is 5.5 years. Now you can figure out the interest you're going to owe is going to be $10,000 times 0.05 times 5.5 years, which gives you a grand total of $2,750. $2,750 is what you would owe at the end of 5.5 years. Okay, so make sure that your T and your R are both in the same unit of measure. Here's another example. So Juanita has deposited $8,000 in a bank for 5 years at a simple interest rate of 6%. How much interest will she receive? How much money will be in her account at the end of those 5 years? We use the simple interest formula with our principal is 8,000, our rate is 0.06, and our time is 5 because it's all in terms of years. So her interest would be 2,400, and of course if we add that to 8,000 at the end of 5 years, she will now have $10,400 in the bank. Compound interest is interest that's paid on both the principal and the previously earned interest. So going back to that example I gave you before, it's where in year 2 you're now paying interest on $105 instead of the original just $100. Interest that's compounded annually is paid once a year, and if we're going to compound interest annually, we have a very simple formula of A, the amount owed, right, is equal to the principal times 1 plus r raised to the power of t. So that's going to be the total amount, right? Either owed if this is borrowed, or the amount in an account. So if you put a bunch of money in an account, that's going to be your P and just let it sit there for t years. This is the total amount. So it's no longer interest, right? We're not solving for I, we're solving for A. It's the total amount. If we want to know interest, then we would have to subtract P from it, and that gives us the leftover, which is just the interest. Here's a simple example. So we've got 6% compounded annually for 5 years. How much money will she have in her account after 5 years, and how much interest will she receive? Plug it into this formula. we get $10,705.80. That's the amount in her account. If we subtract the initial 8,000, we see that she got 2705.80 in interest for those 5 years. Compound interest formula, right? So the previous was simple compound interest, right? Here we've got compound interest that's being compounded more than just annually, right? We've got the same. A is still the amount, P is still the principal, R is still your interest rate expressed as a decimal, T is still time, but here it's always in years, and then N is the number of times it's compounded each year. Here's an example for that. If you put $100 in a bank, pays 5% annual interest, find the future value A after 1 year if the interest is compounded annually, semi-annually, quarterly, monthly, daily. Our principal is 100, our rate's 0.05, our T is 1, right, because we're putting it in there for 1 year. The only thing that's going to change for each of these formulas is N, the number of times it's compounded. For annual compounding, N is just 1. And we can see we get back to that other formula. Because if N is 1, doesn't this just equal P times 1 plus R to the T, right? Because R over 1 is R. N times T is T. And this is our compound interest formula for annual compound interest. And we get $105. However, semi-annually, so now we're compounding twice a year, every 6 months. Now you're putting in N equals 2, right? T equals 1. You get a little bit more, $105.06. Quarterly, $105.09. Monthly, 12 cents. Daily, 13 cents. And then there's actually one more where we could do continuous compounding, but that requires a completely different function that we'll see here in a little bit. But you can see that it does go up, right? It doesn't go up by a lot, 13 cents. You go, yay, big deal, right? But that's only because we had $100. Now think about if you had $10,000 in there, how that 13 cents is now going to be a lot more. Okay, the number E. We already talked about the number E before as being a typical exponential function. And I also mentioned that if we're doing continuous compound interest, that we have a slightly different formula. This is the one, and it involves E. Oftentimes students will try and remember this as A equals PERT, P-E-R-T, right? Principal, P is still principal, A is still the amount after so much time, T is still time in years, R is still your interest rate, again still expressed as a decimal, and then E is a constant. You can check it out in your calculator. It's about 2.7 and some stuff, right? 2.7 blah blah blah. That's E. That's E. Here's an example. Find the amount when a principal of $8,300 is invested at a 7.5% annual rate of interest, compounded continuously for 8 years and 3 months. There's our P. There's our R. We need to convert that 8 years and 3 months to years. So 3 months is a quarter of a year. So that's why we get 8.25. Plug everything in, plug it into your calculator, and there's your answer. At the end of 8.25 years, you would have a little over $15,400 in that account. And then if you subtracted the original 83, you'd see that you made about $7,100 in interest. So it's almost doubled. How about graphing the natural exponential function, which is what the E thing is, right? This is what's called the natural exponential function, or sometimes just called the exponential function, more commonly just referred to as e to the x. So because base E is used so often in so many other applications, the natural sciences, business, all sorts of things, it's kind of referred to as the exponential function. So whenever somebody talks about an exponential function, they're usually talking about e to the x rather than 3 to the x or 1/2 to the x or any of those other versions that are technically exponential functions. Here's how they all compare. You can see that they still travel through the point 0,1, right? Because e to the x is still an exponential function, so it still has that property that it passes through 0,1. It also has the point 1 a, right? 1a. In this case, a is right about there. I told you e is about 2.7, right? Whereas this one is right here at 3, and the blue one is at 2. It has a horizontal asymptote at y equals 0, and it increases up to infinity. It's an ever increasing function because the base e is greater than 1. We can also sketch transformations of these functions just like any other function, right? We know what the basic e to the x function should look like. So now we can figure out what e to the x minus 1 should look like. Well, if e to the x was the original function, if we go to e to the x minus 1, isn't that a shift on the inside, right? That's the inside shift. So that's a left-right shift. And in fact, if it's a minus 1 in here, it's going to shift it to the right. And then what's the plus 2 going to do? Well, that's on the outside, right? That's out here outside of the x. It's not paired up with the x. So that's one of those things that happens on the outside. That's one of those vertical shifts, and that shifts it up by 2. Okay? So the one on the inside moves it to the right by 1 because it's a negative number, and the one on the outside moves it up by 2 because it's a positive number. Just like our other functions, the rules are still the same. Last but not least, we can try and model things in the real world with exponential functions, and as I mentioned before, exponential functions do happen a lot in other disciplines. They do model a lot of things. One of them, one of the more common ones that you'll come across in your career, is growth and decay. Growth of like bacteria in a slide, or radioactive decay of radioactive isotopes. Both of those are modeled very precisely with exponential functions. In this case, a sub 0 is always the initial amount of something, right? The initial amount of bacteria in a slide, or the initial level of radiation. E is still E. T is still time in terms of years. A of t, right? The thing on the left, this is just your function in terms of t, right? It's just like saying f of x, only now we have a function in terms of t because t is the thing that varies. K is not a variable. K is a constant. It's just an unknown that changes from one case to the next. If we have a growth formula, k is going to be greater than 0, and if we have a decay formula, k is going to be less than 0. How about an example? In the year 2000, the human population on the entire planet, right, was approximately 6 billion, and the annual rate of growth was approximately 2.1%. Using the model from the previous slide, we can estimate the population of the world in the following years, 2030, and then we can even estimate backwards to 1990. Well, the year 2000 is going to correspond to when we started, so that's time equals 0. And instead of dealing with big numbers, right, instead of having all those zeros, we're just going to let a sub 0 equal 6, and we're just going to know that it's in billions of people, right? So 6 equals 6 billion. K is our growth rate, or rate of decay. In this case, it's a growth rate, and they told us it was 2.1%, so we write it as a decimal. And then if we want to know what the population is in 2030, we're not going to plug in 2030. We're going to plug in number of years from the starting point. So if 2000 was t equals 0, then 2030 is 30 years beyond that, so we're plugging in a 30. We do all that work and we get 11.265, or roughly 11.265 billion people will be on the planet in 2030. If we work backwards now to get to 1990, that's 10 years before the starting point, so we're plugging in a negative 10. Everything else is still the same, and we get that the population in 1990 should have been 4.86 billion people. The actual population, by the way, was 5.28, so you can see that our model is not too far off. I mean, you might think that's a big difference, but for this kind of simplistic model, it's pretty good. And those are the basics you need to know about exponential functions.